Speakers before coffee is John Ball, and his topic is function spaces and liquid crystals.
Well, thank you very much, and thanks to the organisers of the workshop for letting me speak. Now, I've been listening to all the very interesting lectures very carefully, and I can say confidently that I'm going to be the first person to mention a function space. So Chuck Gartland came very close to mentioning one, but he veered off at the last moment. So I thought it'd be useful, particularly for those who are not sort of professional researchers in PDE, if I said something about the role of function spaces in applied mathematics, and particular for liquid crystals. I think it's sort of easy if you're not a sort of professional in the field to get the wrong impression that function spaces are some sort of technical irritation that have no connection with physics. And I take a very different view, which I'll try to convince you about. Okay. So what are function spaces? So you've got some physical model of something, and it's defined on some region omega in Rn. Perhaps n is 3, or you might be including time, so it might be 4. Some open set with boundary d omega, and you've got some variables given by some vector field defined on omega. So some map from omega to some different dimensional space Rm. And you've got some equations, and you want to say, you've got some model, and you want to say, well, what do I mean by a solution of these equations? And so I claim that in order to do that, you've got to say something about what kind of maps you're going to allow to be solutions. So you might say, right, well, I'm interested in smooth maps, so I might use the function space which is CR of omega, maps from omega to Rm, which are R times continuously differentiable maps. You might want them to be continuous up to the boundary, so you might have CR of omega bar Rm. But because in physics mostly you have energies defined in terms of integrals, it turns out to be very useful to have other kinds of function spaces which are based more on integrals. And the most common are these LP spaces. So LP, the space LP of maps from omega to Rm are the set of U taking omega to Rm with finite norm, and the norm is given down here. So when P is finite, it's just saying that the integral of U to the power P is finite. And when P is infinite, it's saying that U is bounded. U of x is uniformly bounded. The essential sup means that you ignore sets of zero volume. Okay, so now technically you have to say what you mean by the integral. So the integral of choice for mathematicians is the Lebesgue integral. So these are Lebesgue integrable functions. So if you don't know about the Lebesgue integral, it doesn't matter. Just don't worry about it. Okay, now. So that's LP spaces, but of course in problems in physics you also have derivatives. So the spaces of choice, in some sense, for physics are Sobolev spaces, which are spaces based on LP spaces, but with derivatives. So the Sobolev space W1P is the space of maps U in LP such that the gradient of U is in LP. Okay? So the only question is what do you mean by the gradient? Okay, so the gradient, of course, the normal gradient of U at a point x is the linear approximation to the map U at the point x. So it's a linear transformation from Rn to Rm. So it can be identified at each point x with an m by n matrix. Okay, so however we use what's called the weak or distributional derivative, which is defined in a somewhat slick fashion so that it works with integration by parts against a smooth test function. So you take a smooth function phi, which is the zero here means it vanishes together with all its derivatives in a neighborhood of the boundary. And so therefore you certainly can calculate d phi dx alpha. You multiply by ui, and if everything was smooth, that would equal minus the integral of dui dx alpha times phi. That's just integration by parts. Now, if there is an object dui dx alpha which satisfies this, then you call it the weak derivative. Okay, so this is the right way to define derivatives, it seems, and so for example, just so you understand what sort of things can be in a Sobolev space, a continuous piecewise affine function would be in any Sobolev space you want. So something like this. Now, of course, that's not differentiable in the usual sense, but it's fine. Its derivative here is what you think it is. Its derivative is what you think it is, and that derivative is integrable, and that is the weak derivative. And sort of defects in liquid crystals can be thought of as having weak derivatives that are, and so they in certain circumstances can belong to Sobolev spaces. Okay. So I'm going to discuss what appropriate function spaces are in the context of variational models for nematic liquid crystals, specifically the Ozane-Frank and Landau-de Gennes models and potential modifications of these. I mean, similar considerations would apply to dynamic models, but I won't treat them. So just to review things that we've seen many times already in this meeting, the Ozane-Frank theory. So here you're interested in minimizers, maybe local or global, of this functional, which is a quadratic function in the gradient of the unit directive field n. So you're interested in minimizing such a functional subject to the unit vector constraint and suitable boundary conditions. And then we have the Landau-de Gennes theory, which if you so at each point here I'm interested in statics, so I'm just considering things that depend on x. So you have some probability distribution for the molecular orientations rho defined on the unit sphere. So it's symmetric in P. Its integral is 1. Of course, it's non-negative. The Q tensor is this normalized second moment, as we've seen, and it's of course a symmetric trace-free matrix, and its minimum eigenvalue. So it's a 3 by 3 matrix. It has 3 real eigenvalues. Its minimum eigenvalue has to be bigger equal to minus a third, because the matrix Q of x plus 1/3, the identity, is a non-negative matrix. And so we, in the Landau-de Gennes theory, we minimize I theta of Q. Theta is the temperature, viewed as being fixed throughout this, which consists of an integral of a bulk energy of Cb and an elastic energy, subject to suitable boundary conditions. So what do we choose for the bulk energy? Well, we've seen this particular choice several times already, this quartic form with coefficients, positive coefficients alpha, b, and c. And we've also discussed several times that the minimum of this bulk energy over matrices Q, which are symmetric and trace-free, are uniaxial Qs with a constant scalar order parameter. Now, for the elastic energy, let me do the following. So I'm going to take as a sort of representative elastic energy a linear combination of 4 isotropic terms. Now, the first 3 everybody is probably happy with. They're the usual quadratic functions of the gradient of Q, isotropic quadratic functions of the gradient of Q. The fourth one is a little bit controversial. Some people won't like this, but I'll say more about it. If you don't like it, just think that the coefficient of it is 0, and you'll be happy for the moment. Okay. But anyway, it's one of 6 actual cubic terms. It's a sort of representative one. The reason I've chosen one of them is that, I mean, you could put all 6, but the 4 coefficients Li will turn into the 4 Frank coefficients. Now, if you put all the cubic terms in there, there will be a collapse of coefficients onto the 4. But okay, anyway, more about this term later. Okay, so that's an example of what you can do. And let me just remind you how you might go from the Landau-de Gennes to the Ozane-Frank theory. So the idea is that the elastic energy is in some sense small compared to the bulk energy. You want to be near the bottom of the potential well for the bulk energy, and so the bottom of the potential well is given by a uniaxial Q with constant scalar order parameters. So the only unknown is this unit vector n in S2. So you impose this as a constraint. So the bulk energy now is a constant. So you only have the elastic energy. So you just formally take this formula, you you calculate its gradient, you shove it into here, of course, you get a functional which is in terms of n and the gradient of n, and that's exactly the Ozane-Frank energy, and the ki's, the elastic constants in the Ozane-Frank theory, are given in terms of an invertible matrix in terms of the Li. So you can go back and forwards from the ki to the Li. The matrix, of course, depends on S. Okay. Now, so the function space that you use to which solutions are required belong expresses how bad possible singularities of solutions can be. And I claim that it is part of the mathematical model. Okay, now, this may find sort of uncomfortable thought, but I claim that this must be the case because when you change the function space, you change or can change the predictions of the model. So that's QED, right? Therefore, it must be a part of the model. So I'm going to give some examples of this, in particular doing something which I think is anyway interesting, which is to compare liquid crystals to another theory, which is that of nonlinear elasticity. So what is nonlinear elasticity? Well, it's called a potato. I shall always now think of it as a potato. So omega is a subset of R3, which is, so the usual way you do it in elasticity theory is to use the Lagrangian representation. So you take a reference configuration, omega, and you label the particles by the positions x they occupy in this reference configuration. And then in a static deformation, the point x goes to y of x. Okay, so the y takes omega to R3, and if you're, say, working at constant temperature, you're interested in minimizers of the total stored energy or free energy, so I of y, which is an integral of a free energy density that depends on the gradient of y. And of course, the gradient of y is a 3×3 matrix, and we're interested in minimizers of such a functional subject to some boundary conditions, for example, that you specify y on some part of the boundary. So let's compare elasticity with liquid crystals. So first of all, at least in this variational setting, both give rise to multidimensional vectorial problems of the calculus of variations. Now, it's known, this is a long story, and I certainly don't have time to go into it today, that the fundamental convexity condition of the multidimensional calculus of variations is something called quasi-convexity. Okay, it's a sort of mysterious condition. For the purposes of this talk, you should know that it's much more general than convexity, and lying not too much, it is necessary and sufficient for the existence of minimizers, and it's implicated in every fundamental issue in the multidimensional calculus of variations. Now, in elasticity, C is never convex in the gradient of y. It is never convex in the gradient of y, but it may be quasi-convex. And so you can wheel in this theory of quasi-convexity. And for example, for realistic models of rubber, it is quasi-convex. Sometimes it's not quasi-convex. Say for elastic crystals, it's not quasi-convex. But still, even then, quasi-convexity plays a role. So for liquid crystals, it's therefore, in some sense, a little surprising that the behavior on the gradient of Q and the gradient of N is convex. It's as if you're not somehow taking the maximum use of the available mathematics, all right? So, but it's just a little bit surprising to me. You would naturally think that you would arrive at quasi-convex integrals.
So is the elasticity about convex in the nonlinear strain?
No.
Exactly the same form of elasticity. Because that's the theory for the liquid crystal.
No. It's very complicated. They're not. You can't do it in terms of convexity with respect to the strain. No.
But the energy you write down.
I'll write down a bit later an example of an energy that is sort of prototypical. So then you'll see exactly what sort of form it has. So, second comparison. So in both theories, there's a pointwise constraint. So actually in elasticity, there's a global topological constraint that represents that you require that y to be invertible. This is to prevent interpenetration of matter. I mean, if I was omega, you don't want my hand to go through my head and so on. So that leaves a trace of a local constraint, which is that the determinant of the deformation gradient should be strictly positive. And for liquid crystals, we have this pointwise constraint on the eigenvalues of the Q tensor. In some ways, the constraint in elasticity is worse because it's on the top order derivative. So the constraint here is on and we've got derivatives to help us control the constraint in liquid crystals. And in both theories, minimizers can have physically meaningful singularities. So in elasticity, these include jumps in the gradient of y that represent phase boundaries and discontinuities in y that can represent fracture. And in the Ozane-Frank theory, minimizers can have discontinuities in n that represent defects. In the Landau-de Gennes theory, it's not so clear, and I'll say more about this later. So now I want to give you an example where when you change the function space, you change the predictions of the model. So I've chosen to talk about cavitation in elasticity theory. So let's take for the reference configuration the open ball B of radius 1 in R3, and here's a representative kind of form for the elastic energy, which is a kind of caricature. It's a compressible version of the near-Hookean material. So if you wanted more realistic models, you'd add sort of other terms in the gradient of y that had higher powers and so on and so forth. But this is not such a bad prototypical model. So the mu is a positive constant. We've got a convex function of the determinant of the gradient of y. That incidentally kills any convexity with respect to the gradient of y. It blows up as the determinant goes to 0 and as the determinant goes to infinity. And I'm interested in minimizing this integral subject to y on the boundary being lambda x. So that means you just displace the outer boundary of the ball radially outwards by a factor lambda. Okay, so there's a picture of what h looks like. It's supposed to have a sharp local minimum near delta equals 1 to give you an approximation to the incompressibility constraint of elasticity, which is very nearly satisfied. And there's the picture of the boundary conditions and the ball. Okay, now, suppose if you minimize in a space of smooth maps, or indeed in the space W1P for p bigger than or equal to 3, then the unique minimizer of this problem is y star of x is lambda x. In other words, that's just the boundary data. Everything just expands out uniformly. It's the unique minimizer. It exists, and it's the unique minimizer. If, however, you minimize in W12, which is a very reasonable thing to do, because if we go back to the functional, you see we've got the gradient of y squared. So W12 means in particular that the gradient of y is square integrable. So that's a very natural thing to minimize in W12. Of course, the integral might be infinite for something in W12 because of the second term, but that doesn't matter. You're minimizing it. You're only interested in the ones where the energy is finite. And then the minimizer among radial maps is at least, okay, the minimizer is not this homogeneous expansion, and at least among radial maps you can say exactly what it is, and it is given by a deformation with a cavity at the origin. So you see that, yes?
How big is the cavity?
That depends on how big lambda is.
Yeah.
So it's a bifurcation. It's a very kind of degenerate kind of bifurcation, but anyway. Now, so you see that the energy functional, if you like, the model, if you like, stayed the same, right? But we changed the function space and got different predictions. Indeed, the infimum of the energy among smooth maps y is strictly bigger than the infimum among W12 maps y. Okay? This is something that's called the Lavrentiev phenomenon. It's a particularly transparent example of it from elasticity theory. So note that if you change the power in the energy, so instead of having the gradient of y squared, you had gradient of y to the power p, where p was bigger than or equal to 3, then cavitation would be impossible. Okay, because, well, in case p equals 3 is a little more tricky, but when p is bigger than 3, it would mean that the gradient of y was in LP for p bigger than 3, and there's the so-called Sobolev embedding theorem that tells you that any such map is continuous. So it obviously cannot generate a cavity. Yeah?
To what extent is this phenomenon also possibly an expression of topology?
Well, okay. I just say that the defect here has changed the topology. That's clear. Okay, so maybe we just leave it at that. So anyway, so the possible singularities and the topology depend on the growth of the energy as the gradient of y tends to infinity. So let's go back now to the quadratic case. Here we are. So how do we choose the function space? So we could use the recipe that we, if you like, choose the largest space on which the energy is defined. So that would be essentially choosing W12, okay? And then we would have got cavitation. But is in fact W12 the largest such space? Well, I don't think it is. You can always choose something bigger. So it isn't in some sense, because the body could develop fracture surfaces across which y is discontinuous. And, that's something that really happens in solids, that you get real fracture across surfaces. Of course, in cavitation, the fracture surface, if you like, is a point in the reference configuration. But here it's going to be something with actual area. And that's impossible in a Sobolev space. But you could, and people do, instead use functions of bounded variation, in fact some space called SBV, and so you could then take this energy functional, and it allows y to be discontinuous, but of course you in order to recover something like the sort of the Griffith theory of fracture, you would have to add some energy depending on the fracture surface. For example, something that depended on the area of the jump set of y. Okay, so this is been quite a lot of work in this sort of approach to fracture mechanics. So now if you look at this kind of functional, you see it if y is, so in some sense with this functional, you have three different minimizers. If you work in smooth functions, of course this is not here, and you get the homogeneous expansion. If you work in W12, this is 0 because the jump set is 0, and you get cavitation. If you work in BV, you should be able to get, if you pull hard enough, actual fracture. Okay, so the same energy functional, but three different minimizers in three different function spaces. I cannot restrain myself but to tell you about another example, one of my favorite examples, in one dimension. So, I mean, you may think this is a multi-dimensional phenomenon, but actually you get the same thing in one dimension. And here's a terrifying example if you think about the calculus of variations and do the usual sorts of things. So here's an integral of a polynomial. Okay? In U is a scalar. You see it's a convex. It's a strictly convex function of the derivative of du dx. So it's what's called a regular problem of the one-dimensional calculus of variations, because this coefficient epsilon is strictly positive. It has to be quite small. That's a story. And the fact that you have the 28th power, that's another story. But okay, anyway. So but it's a polynomial. It's a perfectly good functional. Now, you're asked to minimize it, subject to u of minus 1 is 1, is minus 1, and u of 1 is 1. So what might you do? We might go and put it on a computer, right? So you'd say a finite element method. You discretize, and you replace a given u by a piecewise affine function. You take a very, very small mesh size. You calculate this. You can even calculate it exactly because it's a polynomial. So you don't have to worry about round-off error. And you put it on the computer, and you get the minimizers. And here they are. So you get two of them. They're beautifully smooth functions. The whole thing converges perfectly, and there we are. That must be the answer, mustn't it? But it's not the answer. That's not the minimizer of this problem. This is the minimizer of the problem, which has a infinite slope at the origin, at which the integrand is infinite. Okay, so you can minimize something by having the integrand infinite somewhere. It's not smooth. That means it is not a weak solution of the Euler-Lagrange equation. That's also worrying. And so these smooth blue curves, they are indeed minimizers of this integral among smooth functions, or among Lipschitz functions, or among W1P functions where P is sufficiently large. And that's a sort of worrying kind of example. And even more worrying examples constructed by Foss of a problem, a two-dimensional problem, where you have a different infimum in every Sobolev space W1P for every real P. Okay, so I hope I've convinced you that the function space changes the predictions of the model. Okay. So what do we do for Ozane-Frank first of all? So here we are. There's the functional again. And since the integrand is quadratic in the gradient of n, the natural function space is W12. So in particular, and more specifically, W12 maps to S2 because n is a unit vector. So that's defined to be exactly the W12 maps from omega to R3, which have range in S2. And so from the point of view of at least having the existence of minimizers under the usual conditions on the Ki, that's fine. So we know we do get minimizers, we even know something about their regularity. And the theory allows point defects, as we've seen. So in particular, it allows the hedgehog. So n of x is x over norm x, sort of illustrated on the right there. So, and of course, the gradient of n of x is given by, well, is in absolute value, it's of order 1 over the radius. Okay, so that when you calculate the gradient of n to the power p, it's of the order 1 over the radius to the p. You have an r squared, which is from the volume term. So this is in W1p, provided p is strictly less than 3. So since we've got p is equal to 2, this has finite energy. Now you have to be a little bit careful in doing this calculation because I've just calculated this as if it's the ordinary derivative. And that's okay, actually, in this example, but in certain other cases you have to be just a little bit careful because it's the weak derivative you have to worry about. You have to worry about, to do this calculation correctly, you've got to worry, you have to remove a little ball around the origin and fool around a bit. Okay, so, okay, in any case, this has finite energy according to this model. So bad news, it can't describe other defects. We've already seen this. So it can't describe disclination. So that's the same thing, but with the director pointing radial outwards from the axis of a cylinder. And here we get that n is in W1p if and only if p is strictly less than 2, but p is equal to 2 for us. And so what that means is that this particular singularity has infinite energy according to this model. And a related piece of bad news is that the theory can't support some apparently good physical boundary conditions. For example, while if you take a ball, say, you can find a map which satisfies homeotropic boundary conditions. So that means perpendicular to the n perpendicular to the surface of the, well, n normal to the boundary. So, for example, the hedgehog is such a thing. So there's no such n, for example, if omega is a cube. So this is a remark of Stephen Bedford, who's here and who's a research student in Oxford. Okay. So what could we do about these problems while retaining some of the advantages of the Ozane-Frank theory? So here are two probably viewed as heretical solutions, but motivated by elasticity. So one thing we could do is to change the growth of the elastic energy as the gradient of n goes to infinity. So we saw that was exactly the problem. I mean, that is the problem. That's exactly why this disconation has infinite energy. It's because the energy grows quadratically as the gradient of n goes to infinity. But if it grew subquadratically, that problem would immediately disappear. And of course, you could easily modify the energy. You could keep it exactly the same, actually, for the gradient of n reasonably small, and then just change it so it has slightly different growth at infinity. Why not? What's wrong with doing that? what's right with it. But would that give a reasonable description of a disconation, for example? So it's analogous, you like, to representing the gradient of n squared by 2 into the root of 1 plus gradient n squared minus 1, which looks the same for the gradient n small. Even more heretical would be to allow n to be discontinuous. Now, we don't usually allow the director to be discontinuous, but why not? That's exactly analogous to the fracture problem in elasticity theory. So you would allow n to be discontinuous in SBV or something. Then you've got to penalize, of course, any jump in n. So obviously you don't want a penalty if n is if the jump in n is 0 or n is pointing in the opposite direction. So you might add some. So there is a jump set that's well defined, and there are limits from either side of the jump set. These limits are n plus and n minus. So when n plus is n plus or minus n minus, you want to have no contribution to the energy, and otherwise you would want a contribution to the energy. Okay. So is this a reasonable thing to do? Or if not, why not? Maybe, but it would again solve the problem about the disconations. Maybe you would just have a jump very, very close to a disconation core, for example. Okay, so these are two possibilities, pragmatic possibilities. Okay, there's another issue about the Ozane-Frank theory, which has already been alluded to, and that is orientability. I mean, in some sense, the derivation I gave to you from the Landau-Dijen theory is not correct, because we went from a uniaxial constraint in which you have a line field, and mysteriously, when we got to the Ozane-Frank theory, this had turned into a vector field, okay, which is not correct. Okay. So this is work with Argier. So okay, so let's go. And so, roughly speaking, so if we have this constrained Landau-Dijen theory where it's uniaxial with a constant scalar order parameter, so that means that at each point of the domain we have a line field, if you like. We've got a pair of antipodal unit vectors. So now, how do we change that into a vector field? Well, that's very easy, of course. I mean, you at each point you've got, if you like, a double-headed arrow, the two possible directions. Everywhere you've got that. So to change into a vector field is very easy. You just, everywhere you just wipe out one of these arrows, and that's turned into a vector field. Okay. But the problem about doing that is that the vector field that you get will have terrible regularity in general, and we want something which has a gradient, for example. So here's the definition that if you have this Q, it's orientable if you can choose the sign of n of x in such a way, so we call that n tilde of x, so it's plus or minus n of x at each point x, in such a way that n tilde is in a Sobolev space. It has a well-defined sort of gradient. So if you like, the original thing Q in this constrained case is a map from omega to lines through the origin. That's the real projective plane, and we're lifting it in the context of Sobolev spaces to a map from omega to S2. If you can do this, then it's said to be orientable. And in fact, if it is orientable, there's exactly two orientations. If you've got one orientation, then the only other orientation is that you reverse all the directions of it. You reverse the direction of every arrow. And so now here's an example of a smooth, non-orientable line field. Okay, so the line field has to be parallel to the dotted lines, and you can very easily check that this is not orientable, because essentially on the left you've got two choices, either pointing to the right or to the left. If you point them to the right, then you get some kind of contradiction in this region here. So even if it's smooth, it needn't be orientable. And there are these other singularities, index 1/2 singularities, and they're not orientable either for a similar reason. And so also this is another one. And so and also the corresponding Q is not in W12. So in some sense, there's two reasons why the Ozane-Frank theory doesn't work for such defects. One, because it's not a vector field; it's a line field. And two, because it's not in W12. But you could, of course, change the growth in the in the Landau-de Gennes theory so that it was subquadratic, and then use a constrained version of that, and then you would get something which was perhaps a reasonable way of describing it within the context of an Ozang-Frank-like theory. So now, if omega is simply connected and Q is in W12, which is the case for these quadratic models, then Q is orientable. So in fact, in simply connected regions, this uniaxial constrained de Gennes theory and the Ozang-Frank theories are equivalent. So a consequence of this theorem is that for the index 1/2 singularity, you can't modify the Q tensor in some core and still satisfy the constraint. Because if you could, you would have a W12 line field in a simply connected region, and therefore it would be orientable. But this is not orientable even when you remove the core. So here's an example.
Can I, I'm sorry.
Yeah.
Question. Go back to that.
Yeah.
So this is it's sick out at infinity. It's not sick near the hole, right?
It's what is
It's not in W12 because
No, because of the hole. Because of the singularity here.
where does the integral diverge when it's not square integrable?
Well, it isn't. I mean, you have to do a calculation, but it's. I mean, obviously, Q is discontinuous near the at the hole. This gradient is infinite at the core. Right. I mean, not when you've got a hole here, of course. I mean, when you remove the hole, of course, everything is smooth. But when you don't remove the when you're back in this situation, here you have a singularity.
Sure,
at the mark, yeah.
so if you do have a hole, you said
I'm just saying you cannot modify things in a core in order to recover finite energy and satisfy the uniaxiality constraint. Okay. That's my statement.
and if the defect is finite, so suppose that disclination line we're not infinite, but we're a closed loop.
Oh, it doesn't matter. Okay.
But far away, then it looks like a point defect.
Well, maybe it does, but okay. Maybe we should talk about it afterwards. So here's a two-dimensional example which sort of illustrates that the Ozang-Frank theory and the uniaxial Landau-de Gennes theory constrained can both have minimizers which are different. So you take I do it as a sort of two-dimensional example. So the region is as shown, so a kind of stadium with two holes removed. We take the one constant theory, so the two theories are then integral gradient of Q squared and the integral of the gradient of N squared in this case. And so if the boundary, so we choose tangent boundary conditions on the outside and free boundary conditions on the two circles. So if you have an orientable deformation, you see that an orientable vector field, so that means that the orientation as you go across some line across the stadium has to go from vertically upwards to vertically downwards. So you can sort of estimate the integral along such a line. It has a sort of lower bound, and then you compare it with this line field, which has gradient 0 in the middle. And so more or less that's a proof that if the two circles are far enough apart, this line field beats any orientable one. So in fact, for M large enough, the minimum energy is unoriented, even though the minimizer among oriented maps. And in fact, you don't need to take M large enough. It's true for any M. Okay, so that shows that in a non-simply connected region, you should sort of worry. Okay, now what do we do in the Landau-de Gennes theory? So here's a theorem of Chuck and Davis. So now you notice L4 is 0, so everybody should be happy. Inequalities on the LIs, and so it tells you that the Landau-de Gennes energy attains a minimum on W12. So W12 with values in symmetric trace-free tensors, subject say to Q given on the boundary by some smooth map. Okay, and so that's good. And in the quartic case, they used elliptic regularity to show that any minimizer is smooth. So this is a part of calculus of variations, which some of you may not be familiar with. Even though you may search for, the larger the space in which you search for a minimum, the easier it is going to be to find one. That's why you want to choose to minimize in a very large space. But once you've got the minimizer, then it may in fact be, and typically is, much smoother than, much more regular than the space in which you minimize. So that's so-called regularity theory. And so here, it's perfect. You get perfect regularity. So even though you're minimizing in W12, it turns out that the minimizer is in fact completely smooth. Okay. What if L4 was not 0? Well, then Palmer-Jumder and I showed that if, for any boundary conditions you like, doesn't matter what they are, if L4 is not 0, then this, and provided this C here, so I should go back to what the hypothesis of the theorem was. So C, B, the bulk energy, was taken to be a continuous bounded below function. For any such of C, the integral is unbounded below. So reminiscent of our discussions about the K13 problem. So on that basis, you should, I think, say that L4 is 0. However, I don't agree with that. Now the reason is that there's no way of controlling the L4 term in terms of the gradient of Q squared, which are the only other terms, more or less, that you've got in the energy. That's why you can't do it. But of course, you can do it if you know that the eigenvalue constraint is satisfied. Because then you see, if you look at the form of this term, it's like QKL ZK ZL, right? So that's bigger than equal to minus a third times Z squared, right? So you can absorb, I mean, if you know that the eigenvalue constraints are satisfied, you can absorb this term in the other terms. So if you modify the inequalities, then you get existence even when L4 is not 0. And this eigenvalue constraint can be ensured if you suppose that the bulk energy blows up as the minimum eigenvalue goes to minus a third. And this was proposed by Ericsson in the context of his theory of liquid crystals. And and in fact, such an CB can be constructed semi-explicitly from the Onsager-Meyer-Saupe model, following a similar prescription to the paper of Katriuk, Wenzel, Luckhurst, and Slukin. And then you have existence of a minimizer even for L4 not equal to 0. And in elasticity, a similar thing is done to ensure that the constraint on the determinant is satisfied. Namely, you assume that the stored energy blows up as the determinant goes to 0, which has the interpretation that you need infinite energy to crush something down to 0 volume. So how are defects described in the Landau-de Gennes model? So according to this regularity result, minimizers are smooth. So in contrast to the Ozane-Frank theory, defects are not described by singularities of Q. And so rather, people tend to think of how you describe the defect instead by discontinuous behavior of the eigenvectors of Q, which can occur when eigenvalues coalesce, even when Q is a smooth function of X. So this was proposed in papers of de Gennes. It's analyzed in papers of Biscari and Paroli, and I sort of learned about this point of view from Argyr Zarnescu. And it's probably a very good point of view, but I just wanted to draw attention to another possibility. If one accepts the idea that the elastic energy might not be quadratic in the gradient of Q. Okay, now there's a whole story about the regularity theory of nonlinear elliptic systems. So essentially, if you have an elliptic system which is quadratic, I mean, if you're trying to minimize some integral that's quadratic in the gradient of your unknown vector, and it's convex in the gradient of the unknown vector, then more or less minimizers are typically smooth. But then the Italian school found various counterexamples to regularity when you do not have when you like, the Euler-Lagrange equations are not linear in the top derivative, so not quadratic in the gradient. And actually, the best example, I was surprised to me. So the weekend, I knew about this theory, but because I knew about it, I'd looked at it last quite some time before I got interested in liquid crystals. So when I went back to it, I was very surprised, actually. Now, there's a very interesting, perhaps the best and most subtle counterexample, is that of Schwerak and Yan, which is in the context of a convex function of the gradient alone of a map from a ball to R5. And so they construct a minimizer which is Lipschitz but not C1, and they construct other similar sorts of things which even have unbounded gradients, which is the unique minimizer of this integral subject to its own smooth boundary values. And blow me down, if you look at it, it is exactly in the context of liquid crystal theory. I mean, as I said, they don't mention liquid crystals, but it's the minimizer is exactly a uniaxial, it's a sort of melting hedgehog, if you like, with the S being the absolute value of X. Now, it's quite a difficult paper to read, actually, but I'm reasonably confident that you could find an psi that is isotropic that would have this as the minimizer. So that's kind of interesting, I think, if that was the case. Of course, in the Landau-Dugen theory, you have also lower order terms, and they could potentially kill such a singularity. But usually, it's the top order terms that determine the nature of singularities. So, I mean, if that was the case, that would mean perhaps that in some circumstances that defects might sometimes be representable as singularities of Q. So summary, claim that the function space is part of the mathematical model, and the same energy functional can have different minimizers in different spaces. Maybe in some contexts you could view the minimizers in the smaller spaces as somehow being metastable states for the theory in the larger space. That's one possibility. And second, it should be a sort of target, I think, to try to derive the appropriate function space at the same time as the energy functional or dynamic equations. Now, this is much easier said than done, of course. For elasticity, there are some atomic to continuum derivations in this spirit using gamma convergence in the school of Breides in particular. Perhaps I might end with some sort of cautionary tale. I'm very interested in all the talks that have been given on trying to derive continuum liquid crystal models from statistical mechanics and such things. And so I don't at all criticize any of these things, firstly because I don't understand them, and secondly because it's an infernally complicated problem and it's incredibly difficult to do anything, so I'm full of admiration. But there is an interesting sort of cautionary tale that one could tell in the context of elasticity theory, where I have a little bit more understanding. Now, if you want to draw the parallel between elasticity theory and liquid crystals, then you should think of the bulk energy in liquid crystals as corresponding to the elastic energy in nonlinear elasticity. Now, the elastic energy for liquid crystals is something that should depend morally on second derivatives of the deformation in elasticity theory. Now, that's important because it represents sort of interfacial energy. So, for example, for Martin-Zittig transformations, you have effectively jumps in the deformation gradient, and they should have those jumps should have an associated energy. And so some people say that should be represented as an integral of second derivatives. So exactly the same questions as Fakulin was asking yesterday are asked in this theory about whether this should be a non-local kind of expression, how you go from a non-local expression to an expression depending on second derivatives, and so on. Now there's a what one might call an expansion method that is done in this context, and it's done the following way. So you have your crystal lattice, and you suppose you've got a smooth deformation, and you use what's called the Born rule which says that the atoms follow the smooth deformation. Okay? You have a small parameter, which is the interatomic spacing. You have some microscopic energy, which you're sort of discrete energy, which you're minimizing. You know, there's all sorts of things you can criticize in these problems. In any case, you have this small parameter, and you expand the energy in the small parameter. And the zero-order term gives you nonlinear elasticity. And the first-order term gives you, under certain circumstances, a quadratic function of the second gradient. So just like the elastic energy in liquid crystals. However, the coefficient of that term is negative. It's called the wrong sign problem. Okay? It's negative, and nobody really believes that this is negative. And there's another method of making the transition from atomic to continuum, which is based on gamma convergence, and that gives you a positive interfacial energy. So it's just that, you know, you have to be careful, I think, with expansion methods when things are varying very rapidly, and I think a lot of subtle things can happen, and that's why I think that sort of rigorous mathematical proofs, if we could find any, which took us from some of these microscopic models to macroscopic ones, would be very valuable. Thank you.
Thank you very much for an interesting talk. Not only a very nice talk, but also bodes well for the coming 6 months of this program, where I think we will find some connection between the two communities here. So wonderful. Can I invite questions? Yes, Chuck.
John, have you thought about function space questions for the Lagrange multiplier field in Oseen-Frank?
Well, I guess okay, the way I formulated that sort of happens automatically, I suppose, right? I mean, we know what the Lagrange multiplier is. It's sort of the...
You just infer it from the solution?
Yeah, it's more or less the gradient of n squared, right? It's...
Well, in the equal constant case, I think...
Oh, an equal constant, yes, of course, right, yes. So I would...
I was thinking more generally.
More generally, no is probably the answer to your question.
Just a couple of observations on the two issues that you mentioned. First of all, on the use of non-convex functions, there is, I think, the PhD thesis of Jim Jenkins and Jerry Erickson uses non-convex functions for the polystatic. And at that, it's not proved, but they suggest that a way to describe the symmetric would be through a fine mixture of the two energies. To the dismay of Jerry Erickson, I don't think that theory had been followed a lot. Perhaps maybe there were the materials that would have fit into that didn't really materialize. And then the other different issue is when you mentioned regularity terms, higher order terms in Oseen-Frank. In fact, this is already what happens in symmetric systems. In fact, Tom Levinsky, he proposed this energy, and also I keep giving you surprises, right? and I think Kujans was also originally in some, maybe afterthought, I'm not quite sure, but Peterson afterthought proposed a higher order term for gradients of the, of the wave function there. And indeed, of course, this is very important in the description of defects in symmetrics, phase boundaries, and it turns out to be also very, very relevant when you do power symmetrics. So there are precedents to this.
Tom, you had a question.
Yes, so I'm a little confused about some of your statements. The language is so different. So when you say, if I look at a strength half disclination, that there's no minimizer over Q, I think that's what you said.
Well, it's not in W12, so it has.
So, but you do admit a solution where I just allow the scalar order parameter to go to 0 at the core, and then the Q.
But that's not okay. I was talking about the constrained theory in which S was a constant.
Yeah, I understand.
Yes, of course, if S could go. Yes, of course, you could do. Yes, of course, you could describe that. That's right.
Or go by axis.
So to speak.
Yeah, that's right. So that's right.
And so you have no objection?
No, absolutely none. Absolutely none. Mind you, I mean, it's experimentally unverified, of course, what happens, right? It means because we don't know what happens at the core, right? So
but if you take the full QIJ...
well, the simulations, that's based on the theory that you happen to believe. So
no, not at all, on microscopic simulations of atoms.
Oh, see, you mean molecular dynamics?
Yeah.
Yeah, well, I think that's very, I'm very interested in that sort of issue, so I agree. Yeah.
But even take the Q theory and just allow the space to have S to 0 and then solve for the constraint that it goes around.
Yeah, well, that's Erickson's theory, yes, more or less, yeah.
And that's okay, isn't it?
Yeah,
There's nothing.
yeah.
So,
I have no objection to that.
so why don't you take that route in your thinking instead of, trying
Well, I mean, that's fine. I've absolutely no objection to that, except that the ozone strength theory has the advantage that, I mean, whatever these dislocation cores are, they're terribly small, and so almost everywhere in the domain, the n isn't, the s is in fact more or less a constant. So, I mean, if you can get away without introducing an extra variable, that's great.
Dave's got a question.
A comment about the L4 term. I think I want them, I need them, and they've been tested experimentally in some cases that if you want to have the bend and splay constants different in a Landau theory, you need invariants of this kind. And they, fitting with measurements, the elastic constants not only involve S squared, but also S cubed, which is the L4 kind of term. So they fit with that. So I think the L4 term really is necessary, and I'm glad you've included it. I think it's useful. I've done a bunch of things with all of those L4-like terms, so I'd like to talk to you about them.
I'm glad you're happy with this.
Stephen, you have a question?
John, I want to draw you back to something you talked about in your elasticity work, which was the role of dynamics for selecting the right function spaces. So have you sort of thought about that question in this context of once you impose a flow, that can actually help you understand what the right function spaces are for minimization questions?
Well, I mean, the general point is that there should be some dynamical equations which have as a Lyapunov function the thing you're trying to minimize. Right? So, I mean, that's a general sort of problem of continuum mechanics. It's more complicated in liquid crystals because it's not just standard continuum mechanics. But that for me is the sort of principle that you would like the second law of thermodynamics to deliver you a Lyapunov function, which looks like what you're trying to minimize. But of course, I mean, there's a huge gap between having the existence of such a Lyapunov function and showing that that dynamically you get the kind of behaviors that approach equilibrium and stability and all over that you hope to get.
So you showed that the uniaxial restriction of the Q theory is not equivalent to the Frank theory, and this is clear. And then you said that it could be, the Frank theory could be generalized among other cases by allowing jump discontinuities, penalizing how different are the two directions. Could it be said maybe that the uniaxial restriction of the Q theory is equivalent to the Frank theory with jump discontinuities?
Because you get a change in orientation, you mean?
Yes,
I was thinking of that.
A very large penalization in which only reverse side,
It might be.
F going to infinity limit.
This is a possibility, but I agree with you.
But it's not.
It's a bit vague. But,
One more quick question. There was somebody else. Yes.
So a lot of the grief seems to come from the derivatives, which ultimately are some expansion of some non-local kernel. Now, one strategy might be to minimize the energy in terms of the non-local kernel and do the gradient expansion after the variation has been carried out. So in nonlinear elasticity, has it been explored how different these two approaches are in terms of the solutions that they produce?
well, it's a very different sort of microscopic model in elasticity. That's the problem. I think it's very difficult to I mean, you don't have. It's not so obvious what this probability density function is and so on. So I mean, it's I wouldn't know the answer to that question, but I think it'd be interesting in liquid crystals. It's perhaps impossible if you could identify some kind of microscopic thing that you were minimizing, over with dependence on x, and then you might be able to wheel in gamma convergence and do something interesting. If you had a sort of small parameter, but I don't know whether that's possible.
I think we better conclude now. Thank you.